surface, we drill a hole, and we end up with a borehole, right? It also gets called the hole, all right? Now, this is the very start of our well, all right? And depending on the rock type, so I'm gonna give us some layers here. So here's a shale. Here's a limestone. And here's a sandstone down here. All right, so at this point, we can just take our drill rig away and we can leave our borehole open. And that gets called open hole, and that is never done on rare occasions. So the rest of what I'm going to talk about now is how we complete the well. All right, so you can have one option is to have your well be open hole, or which just means you just drill it and you leave it. All right, but most of the time we're going to finish the well, and we'll talk about and we'll look at some of the materials we use. But the bottom line is, once you drill a well, you could imagine that you want to try and keep it open. So unless this rock is really competent, what happens is everything just wants to slough into the hole, all right, and fill the hole up with rubble. So we finish it with a variety of different materials. Usually it's either steel pipe or plastic PVC pipe. Those are the two most common things that we're gonna line the hole with. It depends on the application, but I would say anymore in the groundwater industry, the most common material that we're gonna line the hole with is PVC. It doesn't rust, it doesn't degrade over time, for good, better or for worse. And but for the well, that means that it doesn't really rust and start ruining water quality. Now, there's two basic types of pipe that we're going to put down in the ground. One is a pipe that's just a solid pipe, like a normal pipe that you're used to looking at. All right, it's just a solid pipe. So solid pipe in the groundwater world, we're going to call casing. All right. So in general, a little foreshadowing, shales and clays never yield good water. All right. And they're really, oftentimes they're not very structurally sound. And so as an example of our borehole here, we would definitely want to case or drive casing down our hole. And we're not going to plan on getting any water out of the shale, or for this matter, for the limestone in this example. And so we will drive solid pipe or casing from the surface down through this layer. So this is called casing. All right. And this is just, it's unperforated. There's no holes. It's just normal pipe. I think solid is not maybe a good term to use, because it's not like a solid tube. It's got a hole, but it's normal pipe. And that's usually PVC, but it can be steel. Now, in the oil industry, all this is the exact same stuff. They use the same methods of drilling. They use almost the exact same stuff that we use, but they're deep enough that they often use, and they don't care about water quality and things rusting. So They normally use steel, all right? But for us as groundwater, in groundwater, we normally use PVC. All right, the thing about casing is there's no perforations. That means there's no holes sort of laterally in and out of this pipe. It's normal pipe, and water doesn't move from here into the casing. There's no way for it to get in. It's a solid wall, and there's no way for water to get across casing. So if we're down here in the sandstone, which is the area where we want to pump water out of, there has to be some way for the water to get into our pipe. All right. So there's options here. We could just drive casing down into the aquifer and then just leave the bottom open, right? And water could flow up into the bottom of my pipe, right? We call that an open bottom, all right? And it's fine, but there's not very much surface area. It's all you have is the area of the pipe for water to move up into. It's not a lot. So it's a really restrictive way to get water into your pipe. And it's only done if you have a really low flow situation. If you need to produce water in a big way, then we do something else. We put what's called screen in. So screen, and I have some examples I'm going to show here, is a section of pipe, and I will, when I draw screen, I'm going to use these dashes and you'll see why. All right. And screen is pipe that has holes in it. It's perforated. So water can flow in through these holes along the entire length of the screen. So this area down here is called screen. And this is perforated pipe. So here's some examples of screen that I've got from various different applications. Let's start off. Looking at, can everybody see this? Looking at this piece. Let's see if you're going to be able to see. Yeah, I can see it. All right. So you see this, wonder if I can turn the light on here. Oh yeah. Does that make it better or worse? I don't know. How's it look up there? Can you see it?
Yeah.
All right. So this piece up here is normal pipe. It's just normal pipe. But down here, there's slots cut in it. All right. And these slots let water in here, but up here, water can't get through. All right. So this would be casing, and this is screen. All right. So I've got a variety of different kinds of screens. So here, you can start a consulting business, and I have a friend who has one. Might have enough of these samples for all four of you guys to look at them. Well, I'll just throw it up here and then I'll pass it out. For people online, This is casing, this is a sample casing, and it has slots of various diameter or widths. So this is a wide slot here. This is sort of a medium slot here. And this is a finer slot here. All right, so wide, fine. And when I order casing, I tell them what width of slot I want. And basically, you want the biggest one you can get away with, right? The bigger it is, the more water it can flow. But if you're in really fine-grained material and you put big slots in there, the material can just flow into your pipe. All right, so you basically are always trying to get the biggest one you can, but you have to know what kind of material you're finishing your well in. And this is a pretty typical, so this is a 2-inch PVC. This is very typical for groundwater studies, where all we're doing is trying to understand the level of the groundwater or sample groundwater. But if we wanted to produce water, say for Missoula Valley, we need a big well. So this is 4-inch or 6-inch casing, all right, or sorry, screen. All right, and it's PVC again, and it's just now 6 inches. And this would be more of a production well where people are trying to produce water. All right, so 2 main keys here are the casing and the screen. Now, what's important is that if I have a well like this, all right, and I'm screened only, well, let's just, before we get to this question, I have some other terms I want to put out. So we have screen, and the important thing here is the screen is in one aquifer here. And we've decided we wanted to screen this one, all right? So a big part of well design will be where and how big and how long do I want my screen to be, and where and how long and how big do I want my casing to be. So another important part of the well.
Can you share your screen with us again?
Yep. Okay, so here, we've just screened in this one aquifer. Now, another important part of the well is there is a gap. There's a gap in between the rock wall and the casing, right? There's always going to be a gap there. And this gap gets called the annulus. Now, could be that this limestone, somebody spilled a bunch of gasoline in it, and you do not want water from the limestone getting into your well. You only want it out of the sandstone. All right? A really important thing is that water, while it can only come into our well through the screen or through the bottom of the casing, it can move up and down the annulus, right? There's no reason to stop it. So a big thing when we install wells is sealing the annulus, making sure that there's some kind of seal between the rock wall and the casing. So we need some kind of material to fill and seal between the pipe and the rock wall. So this is our sealing material. And this is generally either grout or cement. or bentonite. Does anybody know what bentonite is? It's a kind of clay. It's a special kind of clay, though. Yeah, it's a kind of clay that swells when it gets wet. So if you've ever been out in eastern Montana or in Canada, east of the Rockies, when it rains, nothing drains, all right? And the roads get horribly slick, really, really slick. And that's because they're full of bentonite. And this bentonite, when it gets wet, the clay minerals swell and they just never drain, all right? And so bentonite, you get these dry pellets of bentonite and you can sprinkle them down in your annulus. And then as soon as the water starts to leak in, they swell up and they seal really tight around. So usually we do a bit of grout and a bit of bentonite. Grout is actually pretty permeable, so water can move through cement. Not real fast, but it's not impermeable. But bentonite is a really good seal. So we usually use a combination of grout and bentonite. Okay, so in this well, I have screened, oh, and now I don't want to seal between the rock wall and my screen, right? Because then I would negate putting a screen in. So in between the screen and the rock wall, we put another material. I'm going to go light blue here. So between the rock wall and the screen, we put another material, and this we call sand. This is usually a sand or gravel pack. And this allows water to flow through. And this, the sealing material prevents water flowing. Okay, so now the way our well is constructed, water won't be able to get into our well from these layers, but it will be able to come out of the formation, across the sand pack, into the screen, and out our well. So there's some important features here that we're going to talk about. But if I wanted to know, say, the water level or pressure inside this reservoir, inside the sand reservoir, well, this well would do it. But this well won't tell me anything about the water pressure in these other two wells. It's isolated from them. So the screen location is really important. It tells us what portion of the groundwater we're sampling. So screen determines which portion of the groundwater system we sample or have access to. The cased, where we put casing, we don't have access to it. All right, so well design is basically all about where do I want a case and where do I want screen. And we design wells for a whole bunch of different purposes. All right. So an example might be a Missoula water production well. So all the water that we drink in Missoula comes from the aquifer, right? It's all produced from the groundwater. And we'll get more into this and we'll go look at one of these wellheads. They're pretty boring, but the geology of the Missoula aquifer is like this. So here's the land surface. We've got about 100 feet of gravel and sand. So if we were to drill down beneath our feet, we'd be in about 100 feet of gravel and sand here in Missoula. And then beneath that, we get into clays and sands. So this is gravel and sand. And this is about 100 feet, roughly. And then beneath that in the Missoula Valley, there's like, who knows, but it's something like 1,000 feet of these clays and sands. So this top 100 feet is what we call, when we are going to refer to the Missoula aquifer, we're talking about only the top 100 feet here. So this is the Missoula aquifer. All right, and this is where we get all of our water. So the well here, if I'm designing a well and I want to be able to pump the maximum amount of water, I want as much screen as possible. I want as much surface area as I can get. But we live up here, right? We got cars, we got all kinds of stuff that's polluting at the land surface, tons. So I don't want anything coming from the right near the land surface. So the way these wells usually work in Missoula is I'll have something like 30 feet of surface casing. And that's to isolate me from the land surface. And then I'll have something like 70 feet of screen. All right, and so this well has 70 feet total of this slotted pipe. There's lots of surface area and room for this water to come into our pipe. We pump these at like 1,000 gallons a minute. So they're huge pumps and they're pumping really hard. And this well will yield 1,000 gallons a minute. All right, a lot of water. But that's because it's got a big, long screen. So this would be a production well. Now, We'll learn later, but this well is not very useful for us if we want to know something about the direction in which groundwater is traveling in this aquifer. Because it's essentially sampling the entire aquifer, we can't see differences vertically within the aquifer. And so if we were designing monitoring wells where we were really interested in what the groundwater looked like at a very specific point, then we would put really short screens in over very defined intervals. All right. So the main takeaway, we got to drill to get a hole in the ground. We'll look at how we do that drilling here in a second. And then we're very careful about where we case and where we screen. And the screen determines what portion of the groundwater system that we're going to sample. All right. Groundwater we have, we better know where it's coming from and where it's going to. So really a fundamental problem that groundwater scientists work on is understanding where and sort of how fast groundwater is moving. And so we're going to start talking about how we can figure something like that out right now. And I want to start off with a thought experiment. And okay, so here's the setup. This is a cone, all right, that feeds down to a tube, and it has water in it. Let me use blue, designate the water here. All right, and the water level in this cone stays the same at this level, all right? And it feeds down to a tube. All right, and this tube connects to a cylinder that's full of sand. And then coming out the tube, coming out the cylinder that's full of sand is another tube that hooks to another funnel. And it has water in it, this level, and the water can spill out here, and the water comes into the tube here. And the bottom line is that this is above a table. And the bottom line is that the height of the water, whoa, what did I just do? Marker, what I did. The height of the water here, this is H1 and this is H2, they remain constant. Okay, and there's some amount of water coming out of here, some discharge of water, Q. So this is configuration 1. Now I'm gonna draw configuration 2, which is this same setup. All right, and I'm gonna try and reproduce things as best I can. So I got another cone. All right, coming down. But now I go straight down into the sand column. And then my tube comes back up here. And I got water in here. Okay, and water comes in here, can come in here, and it comes out here, and this is Q2. And that's a perfectly flat line, even though you can't tell from my drawing. And this is the same height. This is H1, and this is H2. All right, so these heights, H1 is the same and H2 are the same. So zoom out here a bit. All right, so the bottom line is the funnels are at the same height, the water is at the same height. It's just that in one, the sand column is pointed up, and in the other, the sand column is pointed down, angled down. All right, and my question to you is, is Q1 bigger than Q2, or is Q2 bigger than Q1? How are Q1 and Q2 related? So how is the discharge between these two configurations related? What do you think? Q1 bigger than Q2, Q2 bigger than Q1, Q1 equal to Q2. So what's the relationship between these two? Okay, so I have an argument for Q2 bigger than Q1. Why do you think that?
Because if it's angled up, then there's like the force of gravity also pushing down on it, so it takes more force to get it up and out. Whenever it's angled down, it's with the gravity, so it takes less to push it out.
Okay, so we might think that gravity has something to do with it, and I would totally agree. But we're not gonna necessarily answer whether Q2 is bigger than Q1 right now. But I would say that gravity is an important player here. Any other thoughts? So Jenna thinks they're gonna be equal. Why? Okay. Jenna's. All right, so Jenna mentioned something, pressure. Let me ask you this. What do you think drives fluid movement through this column? What are the forces driving? So let's scale back even from this thought experiment. What forces cause groundwater to move? Okay. We will definitely, so all right, so we got cohesion and adhesion. We may not delve too far into those today, but they become important for sure. What are other things that cause fluid to move? Pressure. What else? why does water move downstream in a river? Why is it moving?
The slope.
Yeah, the slope, but the driving force is gravity. Gravity is pulling it down slope. So if we come back up and think about our experiment here, we might think, well, what is causing things to move through this column? Why would water move through this column? Well, it's probably got something to do with pressure. Probably got something to do with gravity. What else? Can you think of any other things? Cohesion and adhesion. I'm going to say become really important when our sand column is not saturated. But if it's fully saturated with water, become negligible. They are a force that they are a resistive force, but and we'll talk about that later. But they're not necessarily a driving force. So any other things you guys could think of that might drive or move this, cause the water to move? Okay, well, if nobody's got anything else, pressure and gravity. All right, I think we could think about those being important forces. All right. So let's do a little bit of unit analysis and statics here. Okay. Let me find my notes. Force. Physics 1, what is force equal to? Okay, you're close. F equals ma. I think it's the most useful equation on the planet. F equals ma. mg is just a subset of this. G is the acceleration due to gravity. All right, so force is equal to mass times acceleration. I want to do some unit analysis. So what are the units here of force? Well, what's the unit? Let's use SI units. We'll operate in a sane world for a little while, and then we'll get into the insane world. All right, so what's the unit of mass? All right, what's the unit of acceleration? Kilograms, meters per second squared. What's this also known as? A Newton. All right, so this is force. F equals ma. Okay. Energy, also known as work. What's the equation for energy? Force times displacement or distance? FD. All right, what are the units of this? So our units of force were kilograms, meters per second squared. What's the unit of distance? Meters. So energy has this unit, kilogram, meter squared per second squared. This is also known as a joule. Now, a particularly useful thing for us in order to understand fluid movement is going to be, because fluids, it's really hard to sort of think about a very, we're not thinking about a single body mass. So when you think of like F equals ma, you're classically thinking of like some block that you accelerate or something. In fluids, we're accelerating this fluid. So we're often going to normalize by some quantity, and usually it's going to be volume. All right. So an important thing for us might be the energy per unit volume. Energy per volume. Right? And you can think about this as like you've got a cubic meter of water, right? You got a cube of 1 meter by 1 meter by 1 meter of water, and we want to know how much energy that 1 cube has. All right, it's the energy per meter cubed of water. That would be kilograms, meters squared, seconds squared, divided by volume, so multiplied by 1 over meters cubed. And this is kilograms. Those guys cancel. So we have per, oh, this is squared, meter second squared. Kilograms per meter second squared. Let me just kind of highlight that. That is energy per unit volume. Okay. So energy you can think of as the total amount of driving force. It's the total amount of force that we have to accomplish work, right? So energy is going to be really important. And for us in fluid statics, energy per, or in fluid dynamics, energy per unit volume is a really important thing for us to think about. All right, so we talked about this a little earlier, but let's start thinking about what pressure is. So what was the definition of pressure? You guys remember? It's force per unit area. And remember, when I stood on the podium, my weight, all right, which is my force times the acceleration of gravity, all right, or my mass times the acceleration of gravity, that's the force that I'm exerting. That force distributed over the entire surface area of the podium is the pressure. All right. So pressure defined as force per unit area. All right. And let's look at the units here. What were the units of force again? Not newtons, the basic ones. Yeah, kilograms, meters per second squared. And then divided by area, so times 1/meters squared. So these two cancel, and we end up with kilograms per meter second squared. Wait, what does that look exactly like? Okay, so pressure, take home, number one, pressure is a measurement. This is pressure energy per unit volume. All right. So one of the things that I want to drive home is that when we want to think about how water moves, essentially we need to think about an energy gradient. All right. Now, what do you think? Does water move from high energy to low energy, or from low energy to high energy? Everything moves down energy gradient. All right. The only way to get something to move up energy gradient is to pour more energy into it. So water always moves from high energy to low energy. So for example, high pressure to low pressure, high energy per unit volume to lower energy per unit volume. All right. So pressure is a measurement of a very specific kind of energy, but the energy provided by the height or by the height of the fluid column above it. So let's talk about fluid pressure. Oh, another thing that I wanna make point out with pressure here. Pressure is essentially, well, let's do this. Let's talk about fluid pressure. And let's consider we got a graduated cylinder here, or a well, whatever, a long column of water. And it's got water in it. And the height of this water, I'm going to denote by psi. And it has an area A. So I want to calculate the pressure at this point P. Let me give it another symbol. Let's call it point A. I want to know the pressure at point A, which is down at the base of my column. Okay, so how do I calculate? So remember that P is equal to F divided by A. All right, which is equal to mass times acceleration over the area. So what's the mass of, what's the mass? Let's just give this a volume of water V. What is the mass of water here? Sure, sure. So the mass of water, density of water, times the volume of water. If I sort of break this out down here, what's the definition of density? Kilogram per meter cubed. If I multiply this by the volume, which is meter cubed, right? Then the meter cubed will cancel and I'll end up with kilograms mass, right? So rho times V is equal to kilograms over meter cubed times the volume times meter cubed. I end up with mass. All right, so that's the mass. What's the acceleration here? Gravity. Over A. Right, so this is mass times acceleration over the area. Now, I'm gonna do one more step here. And I'm gonna write the volume of water as the height of the water column, psi, times the area. That's just the volume of a cylinder. I just take the area here of the circle and I multiply it by the length. So the volume, I just break it out into psi over A times G over A. And then I really quickly can just get rid of the A's and I get this equation. P is equal to rho water psi G. Okay, so this equation allows me to say, hey, I can calculate the pressure at point A really easily. I just take the density of water, I multiply it by gravity, and then I multiply it by the height of the water column above that point. So it's density times the height of the water column above my point A. So PA would be density times this psi, and I multiply it by gravity. All right, so this is our fundamental equation for pressure. It assumes one thing. It assumes that my liquid has a constant density. All right, so I made this assumption actually when I inserted this. So I'm assuming So for variable density, oh, I don't need to do that. For variable density, I could think about adding up. Let's say my density changed with height in my column, right? I had less dense water up here and I had more dense water down here. I could think about just adding up the force from a whole bunch of little disks, all right, of infinitesimal size. And as soon as I do that, you know, I'm going to start writing up integrals or differentials. But the variable density equation for the pressure at A would be the integral from 0 to psi rho g d psi. All right. I just am going to calculate essentially the weight of a whole bunch of little disks. All right. And I could probably assume gravity is constant and I could pull the g out of this. Oh, rho d psi. That's not psi. And I would have to know how the density changes as a function of height here. All right. For the most part in this class, we're just going to assume constant density. For groundwater, that's a good assumption. So just know that for the most part, this is a very safe way to calculate pressure. But if you wanted to know how pressure varied as a function of depth, or how pressure varies, is calculated in the case where we don't have constant density fluid, you got to integrate over the pressure, over the height. D psi? No, this is a differential, so it's a little, yeah, the D stands for like dx or dy, so it's like a differential. This could be dz here, but I've used psi. Okay. So before we go, I think I have just enough time to introduce this idea of total fluid potential. And we've already alluded to it, but the idea is that water moves from high energy per unit volume to low energy per unit volume. And what we're interested in doing is if we're in a groundwater system, and we were to sort of look at a cube of water here, we want to think about all the sources of energy that might move this block of water, or that this block of water might have. And I'm going to say that this block is some height up, and it is some depth below the water table. Psi. Right, so the height above some arbitrary datum, this is some arbitrary datum of z equals to 0. The height above that, the cube is some height z above that, and it's some depth psi below the water table. All right, so what are the sources of energy that this cube has? We've already sort of talked about 2 of them. What were they? What were sources of energy that move this cube? Gravity and pressure. So pressure, energy. Now, think back to physics 1. What is the energy associated with gravity? What do we call it? Like if I was on top of a mountain, how would you measure my energy that I have from gravity? I've worked really hard to get up there. How would you measure my energy due to gravity? And what would you call it? Well, it would definitely have something to do with elevation, I agree. But elevation alone doesn't measure energy. It has something to do with elevation, and it has something to do with mass, and it has something to do with gravity. Potential energy, right? Mass times gravity times elevation. So pressure, energy. Potential energy. And I'm going to put in parentheses, this is really the energy due to gravity. Pressure energy, potential energy. What's another source of energy this cube might have? Like if it's moving, what do we call that? Right, kinetic energy. All right, so there's a famous equation in fluid dynamics. It's called Bernoulli's equation. And it says, okay, if I make a bunch of assumptions, and one of them is that my fluid's moving laminarly, it's not turbulent. The other one is that it's incompressible so that it doesn't change density as it moves. And the third one that's important for us is it's inviscid. So cohesion and adhesion are something we're not going to consider. All right. Then the only real sources of energy in my cube are these 3 that we've talked about. All right. So if I assume laminar inviscid incompressible flow. All right. What this means is the water's moving slow. It's okay for groundwater. Inviscid, it's kind of not okay, but we're going to deal with that with a fudge factor. All right. Incompressible, water's pretty much incompressible. All right. It's slightly, the density changes slightly if you're at really high pressures, but not much. All right. But the bottom line, these are pretty okay assumptions for groundwater. then I can sum all the energy in my cube as the pressure energy, P, plus the potential energy, rho G Z, plus the kinetic energy, 1/2 rho V squared. So this is pressure energy. This is gravitational energy. And this is kinetic energy. And what Bernoulli's equation says is that these three energies are constant along a flow path. All right. So what it means is if I change, let's say I reduce the pressure, if I'm on a flow path, if my pressure reduces and if I'm at the same elevation, but I go from a high pressure to a low pressure point, then I have to increase this guy in order for these to all stay the same. If this one goes down, this one stays the same, this one's neutral, then this one has to go up. All right? So it just allows me to think about how energy is transferred within a fluid. All right? Well, if I dropped both pressure and I dropped my gravitational potential, then I could increase velocity a lot. If I dropped pressure and increased gravity at the same rate, then my velocity wouldn't change at all. They're always the same. So this Bernoulli's equation allows us to have this idea that we can think about the total energy in our fluid and how it's transitioned between these three types: pressure, gravity, and kinetic. All right. And remember that each one of these is a energy per unit volume. Okay, so it's 9:50. We're at the end of class, so we'll end with Bernoulli's equation. But just know that it's a way of summing all the energy in my cube. All right, for those of you here, I have assignment number 2 handout. For those of you on Zoom, I will post it on Moodle, or you can come by my office and grab assignment 2. And other than that, we will see you on Thursday. Okay, have a good day.
Oh, I had a question.
Yes, Finch.
How should I turn in the homework assignment that was due today? My quarantine ends on Friday, so I can like turn it in person on Tuesday, if you'd prefer that. But like, I don't really know.
Let's see. Do you have a scanner or your phone? You could just take pictures,
Okay.
turn it in via PDF. Let's see. Do you have a scanner at home?
I don't.
I think probably the best thing to do then is just to try and take nice photos of each one. Then you should be able to turn those all into a single PDF. What kind of, are you on a Mac or a PC?
I don't own a computer. I'm only on my phone.
Oh, you are only on your phone.
Yeah.
Adobe Scan. That's what Jenna tells me on her phone.
Okay.
And you should be able to turn it. Yeah, that should turn it into a PDF, and then you can just submit on Moodle. So I will, or email it to me.
Okay. And then also I thought it was due on Thursday, so I'm gonna have it late anyway. Is it no, that's fine for me to turn it on Thursday?
Yeah,
Just
turn
over
it in on
email?
Thursday. Yep.
Okay, cool. Sorry about that. I misread the syllabus.
No worries. Just turn it in then.
All right. Have a good one.
Yeah, you too.